Thanks to the organizers for putting together such an amazing workshop. It's really exciting to see so many people interested in GANs. And also, I have to say, this is joint work with my colleagues, Boton Seke and Ryota Tomioka. And it's a great pleasure to go to work every day and work with such brilliant colleagues. So this is a NIPS paper. It was presented on Wednesday evening in the poster session, but it's also an archive. You can find it easily. So I think of GANs maybe perhaps slightly differently than other presenters here. I think of them as just a tool to estimate probabilistic models, and not limited to generative probabilistic models, but also including discriminative probabilistic models. So what are the general goals when we want to estimate a probabilistic model? Well, one of the standard assumptions in machine learning is that we assume there is a true distribution Q somewhere in the world, and we get to observe that distribution through IID samples. And to fit a model to this distribution, we typically propose a parametric class of possibilities, a parametric class of models. And then we can have parameters, and these parameters identify individual models in this class of models. So you could think of all the neural network parameters together when you fix them, identifying one probabilistic model. And then the task is to navigate the space of models and to identify a good one, and this is called estimation. And to do this, we essentially have to think about how we measure the difference between two different distributions, P and Q. And if we can measure the difference, then we can minimize that distance, and that is called then model fitting or estimation. So the remainder of the talk will be on various ways to do that. One of the key things here is to think about further assumptions that we are going to make about all the models in this model class P. So typically you can think of models that you can sample from, tractable sampling. But there are many models, for example, random field models or graphical models, for which it may not be possible to obtain exact samples. Or you can make other assumptions, such that you can compute certain gradients for models of this model class. And perhaps one strong assumption is that you have a tractable likelihood function. So for every instance in your model class, you can compute the likelihood or log likelihood pointwise. So what's interesting about GAN-type models is you have a parametric model, you have a parametric probabilistic model. So it's actually the original model from Ian Goodfellow's 2014 paper. But it's constructed in a very different way to, say, a graphical model. It's constructed in the following way. It consumes a random vector from some standard distribution, and this distribution doesn't have any parameters. So in this case, for example, a 100-dimensional uniform random vector. And then it transforms this random vector through a sequence of transformations, in general nonlinear transformations. And whatever comes out of this sequence of deterministic transformations is a sample from your model. So in this case, a small image. So this is a sound probabilistic model. You can essentially push a button and you obtain one exact sample from it. But it's also what I call a likelihood-free model, because although there exists a likelihood function, it is in generally not tractable to compute the likelihood function. And the reason is that many possible inputs could be mapped to the same output. And to compute a pointwise likelihood, you would have to find the pre-image. You would have to find all the points that map to this output. And that's computationally not tractable. So that's why the GAN models have a different flavor to other probabilistic models, such as, for example, models you see in variational autoencoders or graphical models. So here's a rough categorization following the picture that Arthur had on different methods that have been used successfully to estimate probabilistic models or define distances between two probabilistic models. So one is a class of integral probability metrics that Arthur has already mentioned. If you are interested in that, I can really recommend a review paper from Bharat Sripedumbudur from 2010 in JMLR. And those distances are defined by taking a difference of expectations, and each expectation is from one of the distributions. So Q is the real distribution, the true distribution that you want to fit, and P is your model distribution in this case. And you take the supremum over this difference over a class of functions. And the class of functions map from the observation space to a scalar. So depending on the structure of this function class, f, calligraphic f, you get different integral probability metrics. So if you choose this to be reproducing kernel Hilbert space, so adopt a kernel approach as Arthur has done, then you obtain the kernel MMD, the kernel maximum mean discrepancy. But you can use other structured function classes, and then you obtain things like the Wasserstein distance. And there was also a NIPS paper this year on disco nets, where you can start with a loss function and derive a suitable integral probability metric. But the key thing here is really that both distributions P and Q appear in expectation form, and that directly suggests a way to approximate that using samples. A second class of methods that we use to estimate probabilistic models are so-called proper scoring rules. You may not have heard the term before, but you certainly have heard of the method of maximum likelihood. So maximum likelihood is one instance of a proper scoring rule. So a proper scoring rule is a loss function for distributions. So it's a function that takes as first argument a distribution, in this case P, and as second argument a realization, in this case from the true distribution. And then gives a score of how well this distribution fits that realization. And it does so in the way that only when you have identified the true distribution, you have the smallest possible score that you can achieve. So the log likelihood is one instance. There are other scores such as the Brier score, the spherical score, the quadratic score. There are very many other variations of this. And note that the structure here is slightly different. You assume that your model distribution is available in a richer form, for example, as a density function. For example, in the log likelihood computation, you actually need to compute the log likelihood pointwise. But the second argument is just an expectation over the samples of the true distribution. So that's why we can apply maximum likelihood even only if we have samples from the true distribution. And the third class of ways to define a distance between distributions are f-divergences. And they are, if you can think of them as a generalization of the Kullback-Leibler divergence, where you take an expectation with respect to one distribution Q and then a function, a convex function of a likelihood ratio. So here you need both distributions, P and Q, in the form of a density function. And in general, we don't have the density function of the true distributions that generated the data. So it seems like not possible to apply this to actually estimate models. So instances of that are probably the most popular divergences we know of, the Kullback-Leibler divergence in both directions, the Jensen-Shannon divergence, the total variation divergence, and the Pearson chi-square divergence, but there are many more, infinitely many. For every convex function f, there exists an f-divergence. So let's look at the structure here of from left to right. We increasingly need a more fine access to these different distributions. And I think of GANs as a way to convert it from the difficult case, to convert f-divergences from a difficult formulation where you need really a likelihood ratio to the simple case where you just need a difference of expectations. And the first known paper that has done this transformation that I know of is from Xuanlong Nguyen in 2010, together with Martin Wainwright and Michael Jordan. And a year afterwards, there's also an extensive analysis in Mark Reed and Bob Williamson's JMLR paper in 2011. But they were only interested in estimating f-divergences, not using these estimates to actually fit a model. And then Ian Goodfellow in 2014 introduced the GAN approach for the particular case of the Jensen-Shannon divergence to actually fit a deep generative model. This is really exciting, and the typical picture of how GAN is motivated is this picture, or a similar picture. You've probably seen it like a number of times already. You have this generator distribution parameterized by some parameter theta. You have the training set, and then you have an additional auxiliary neural network that is a binary classifier called the adversary, and out comes a saddle point objective in which the generator tries to fool the discriminator, and the discriminator tries to do a good job at classifying where the samples come from. So okay, so that's a typical way how GAN is formulated. Now, our NIPS paper this year makes the following contribution. So we generalize this GAN objective to the class of f-divergences. And we simplify also the GAN algorithm and provide a local convergence proof. So let's go through these step by step. So first, a quick reminder, our goal is to somehow get these two distributions to agree, the true world distribution Q and the model distribution P. But the problem is, even for the GAN model, we only have access to samples. And so we try to find a procedure that somehow moves them on top of each other. So the most principal starting point is just start with a definition of an f-divergence. So let's go through that. So there will be a few equations now, but it's actually quite elementary, and you can rederive it later from on paper by yourself, because it's rather simple steps. So here's a definition of the f-divergence again. We have distribution Q and P, and f is called the generator function, and it needs to be convex. And for an argument of a 1, so it's a scalar function, for an argument of 1, it needs to return 0. And you can see that if the argument is 1, essentially you have matched the density perfectly at that point, and if you match it perfectly at every point, then the whole divergence will be 0. So typically, the generator function has a very simple structure, for example, logarithm or negative of a logarithm, in this case, a quadratic form. And this realizes in different f-divergences. So now one of the properties of convex analysis, really elementary property of convex analysis, is that any scalar convex function has a Fenchel conjugate. It's called a Fenchel conjugate function. And this Fenchel conjugate function defines a lower bound, a pointwise lower bound on this function f. So I will go back to this formula in a second, but here's the intuition that any convex function can be represented as a supremum over linear functions. So here's a convex function, and here's a lower bound on the convex function, which is linear. And for every point, I can construct a tight lower bound. And if I take the supremum over infinitely many lower bounds, then I can exactly reconstruct this function. So taking the supremum is exactly what this formula does. And the intercept with the y-axis is essentially what this f-star function describes. So it's just an equivalent representation of a convex function. So now let's put this representation of a convex function into the definition of the f-divergence and see what happens. So here's the f-divergence again, and we just plug in this definition. So nothing has happened yet. It's an exactly equivalent way to represent f-divergences. Now what we would like to do is to move the supremum somehow out of the integral sign. The problem is that inside the supremum, x is a constant. It's a qualified variable, so it's a constant. And therefore, the supremum is pointwise for this particular x. So what we need to do is we need to introduce a function, capital T, which allows us to go from this pointwise evaluation and to take the supremum out of the integral. So this is what happens in this step. We put the supremum outside. And in general, this function class, calligraphic T, will not be able to represent every pointwise supremum exactly. So this gives us a lower bound on the divergence. If the function class is rich enough, then it's still an equality. But another thing that happens is if you look at the equation inside the supremum, there is a ratio of Q and P, and the P cancels with a P of x that is outside the supremum. So what's left after we put the supremum outside the integral sign is two simple expectations, 1 over Q and 1 over P. And the function f disappears by the supremum representation, and we introduce a function f star. So this is the final form. It's a supremum over the difference of two expectations. And because we now have expectations, we can use a sample-based approximation, which is possible now, and we couldn't use this before in the original definition of the f-divergence. So if you compare that now to the original GAN objective, we have a more general objective function which exactly recovers GAN as a special case. So that's good. It's essentially another derivation of the GAN objective starting from an f-divergence. We can look at this particular functional form of f star. There's one caveat though. The f star function for some of the divergences is only defined for certain arguments, so for certain ranges, so not on the entire real line. And therefore we have to, in practice, when we use a neural network, we first have to map a real valued output into this domain. So here's a visualization, and we spell out a lot of details in the paper. So if you want to implement this, essentially you download any GAN implementation, you have to change 2 or 3 lines of code, and you can use the tables we provide in the paper with our recommended mappings to the right domain. Okay, so that was the generalization of the GAN objective to the general f-divergence. Now let's look at the algorithm. So the original algorithm that was proposed by Ian was of a double loop structure. So you have the outer minimization and then you have the inner maximization. But in practice nobody does it because A, it would be too expensive, and there are other problems as well. And so it's a question of what does the algorithm that people actually implement in practice, can you say anything about their convergence guarantees or their behavior? And indeed there were some results, but it's kind of, still the intuition of this double loop structure is perhaps misleading. So what we propose in this paper is a very simple algorithm, actually the simplest algorithm you can think of. You compute this objective function that I had on the slide. So you take a batch of real samples from the training set, a batch of generated samples, you put this in a discriminator, you sum the 2 different terms of the different expectations, you do 1 backprop, and then you do a gradient ascent step in the dimensions of the discriminator, in the generator, and a gradient descent step in the discriminator. So it's the most simple algorithm to implement, and it's the most simple algorithm you can think of. But does this converge? So we provide a local convergence theorem. Unfortunately, it's only local. So essentially, what we say is, if you're already in the vicinity of a saddle point, and all the right dimensions are strongly convex and all the right dimensions are strongly concave, then this algorithm has a geometric rate of convergence that we propose. And the rate of convergence depends on exactly how strongly convex the function is. So the bigger problem is, of course, how to get into the vicinity of a saddle point. So it's just a kind of a result that says this algorithm is not stupid, but the bigger problem is, of course, how to get in that region. But here's an illustration of what happens locally. So these are 2 functions, both strictly convex and strictly concave in the right dimensions, initialized from various points, and you see that the algorithm correctly converges to the saddle point. So I think there's room for thinking about efficient algorithms for finding saddle points and treating the saddle point problem really as a problem you want to solve. So there's maybe room for improvement here in terms of algorithms. Okay, let me go to the experiments. We did a couple of experiments in the paper. I'll only mention 2 experiments here. One is on a very synthetic experiment. It's an experiment that was first done in 2005 by Tom Minka, where he analyzed the effect of different alpha divergences on message passing schemes in graphical models. The task here is essentially that you have a true distribution which is a mixture of 2 normals on the real line, and your model distribution is a single univariate normal distribution. So you're in the misspecified setting where you can't fit the true distribution, and then the effect of the divergence should be large, and we can observe the differences and different behavior of the different divergences. So, and indeed this is what we find. On the left you see the true distribution, the mixture of normals, and the fit. And because it's a univariate problem, we can actually exhaustively search over the best fit using numerical integration as well. So this is also a confirmation that our algorithm works in this very simple setting. And there's now a difference in behavior. For example, the Kullback-Leibler divergence has a so-called moment matching property. So it matches, in this case, the first and second moments. Whereas a reverse Kullback-Leibler divergence, when you minimize a reverse Kullback-Leibler divergence, it has a mode-seeking property, so it fits more to the modes of the distribution. And this is precisely what we observe in our experiments. This essentially gives us some confidence that our algorithm works and that the derivation was correct. The second experiment that we do is just to use the DC-GAN architecture on the LSUN dataset, but training it on various f-divergences. So I really appreciated Sumi's talk on all the heuristics that you have to use for making GANs work. I think it's a very fair assessment and important also to communicate at a meeting like this. And similarly, we use batch normalization, and gradient clipping in particular was important, and Adam. And also we profit, of course, from Alec Redford's excellent DC-GAN architecture. So we fit it to images of classrooms. This is the architecture as a reminder. It's a simple deconvolution or transposed convolution stack. And the final image in our case is 96 by 96 instead of 64 by 64. And the interesting finding is that all divergences work, but visually we couldn't tell differences in quality between the different divergences. So here's another visualization. This is for a model that was trained on Kullback-Leibler divergence. And what I visualize here is a random trajectory through the latent space that is generated by sampling some control points and then using a Bézier spline curve, a circular Bézier spline curve, to provide an endless circle. It's a bit hypnotic if you watch it too long. But what you can see, interestingly, is the model has definitely some smooth structure. So you see whiteboards, blackboards, sometimes you see heads of students and tables. It's typical classroom images. It's not perfect. This was maybe state of the art a year ago or even a bit more than a year ago. And it's very impressive to see the progress that the field has made in more and more models of images. Let me say at this point also that why do we actually fit images? Is this like the thing we want to do? I think images are very nice as a proxy task for two reasons. The first of all, we are evolutionarily tuned to be able to assess quickly whether an image looks realistic. We are not tuned to judge whether some biological data or financial data or other data source that also has a rich structure is realistic. So by looking at images, we can actually quickly assess roughly the quality of our models. That's one reason, and the second reason is images are living on a high dimensional distribution on manifolds. So if we have techniques that can automatically discover structure of these manifolds, as well as learn distributions on them, I think that is very much progress for the field as a whole, and we can hope that these techniques transfer to other domains. So that's why fitting images is not the end goal, but it's a good intermediate step. So the interesting bit is now, there have been some papers in the last year, or some works in the last year, that say for fitting images, actually some divergences should really be better than other divergences. And our empirical findings for this particular special case of the LSUN data set, using the DC-GAN architectures, using the particular choices of divergence in our implementation and the hacks that we used, for these choices we don't observe these differences. So why is there something wrong with the existing works or with our method? So I don't have like a full conclusion, and I would like to just throw this out there because I think it's an interesting question. That my current intuition is we have this picture in mind where we have the true distribution Q, and it's outside our model class, so our model is a bit wrong, and therefore the divergence really matters, should matter, and our model will select different. Our divergence will select different representative models that fit certain statistics better than others. But I think more realistically, the true distribution is quite far away. And we essentially project on more or less a very similar point on our restricted model class. So the model has a very strong inductive bias, and I think that is one of the reasons why we don't observe so much differences. But I would be very happy to be proven wrong. So that brings me almost to the end of the talk. I think in terms of future directions, you have heard a lot already about the training difficulties of GANs. It's real, so it's exciting. GANs are exciting, but the training difficulties are real. So there are various hacks. I think some of the more exciting advances are made very recently. There's an ICLR submission by Kasper Sonderby and people from Twitter Cortex, as well as a workshop paper here, and I think it's also an ICLR submission by Martin Ajovsky and Leon Boutou. And what they say is, if you think about the form of the f-divergence, if your divergence, so the form of the f-divergence is to integrate over the whole space. So you integrate over one of the distribution, which is defined on the whole space with respect to some base measure. Then what actually happens when you train GANs is that you collapse the dimensionality. Your density does no longer live on the full dimensional space. And the two densities, the true distribution and your model distribution, they actually do not intersect at all. Their support doesn't intersect. So it's even questionable whether you can define a divergence function, let alone optimize it. And so the fix to that, proposed in these two works, is to essentially convolve your distribution before you feed it to the discriminator. You convolve it with a Gaussian, and therefore you restore the full dimensionality. And so this is an interesting observation. I think there is some more room left, and my hope is that in the next 6 to 12 months, somebody will figure out a really robust, foolproof way to train GANs, and then we can just use it as a building block in larger models, and it will be lots more fun. From our work in particular, from the f-divergence work, I think an interesting bit is now we have access to the Kullback-Leibler divergence. So there are two interesting consequences. One is that you can now do, when you can optimize the Kullback-Leibler divergence, you can do maximum likelihood. So you can now do approximate maximum likelihood in a likelihood-free setting. And that is a topic that many people have tried for in a field of statistics and machine learning called approximate Bayesian computation. So maybe there are some implications as well on approximate Bayesian computation. And the reverse Kullback-Leibler divergence is also interesting because we have used that in the machine learning community to great extent in variational inference. So now perhaps we can use GANs also for variational posterior inference in big models. And in terms of applications, there are some early works on using GANs for discrete data. I think there's a lot more work to do, and would be exciting to extend GAN models or GAN-type models to text data, and to explore the links to reinforcement learning, either in terms of methods to improve stability, or in terms of applications of GANs to model-based reinforcement learning. I think it's a very exciting time, and I'm looking forward to all the great work that all of you will do on this topic. So thank you very much for your attention.
Have time for a question or two?
Here. Hi, nice talk, and great work. So I have a short question about your intuition about the last slide. So what is the amount of divergence after it is finished? So I'm asking this because if your intuition is right, as far as I understood, the divergence should be quite large for everything. So
yeah.
How about
So the problem is that the estimates of the f-divergence is actually not very accurate. So it's a finite sample effect. You would hope that this would go away, and also it could be an effect of this manifold collapsing. So I don't trust the divergence estimates at all from our f-GAN approach, or from the GAN approach, right? You can't trust the divergence estimates, actually. That's the problem, yeah.
Hi. Great talk. I wanted to point out something that the simultaneous gradient step algorithm, actually in the original implementation we released with the 2014 GAN manuscript, we were actually doing this. It was a bit of a convoluted implementation, but we were actually doing this mostly just out of a desire to keep the GPU occupied. But it is a very nice result to see that at least locally it's not a crazy thing to do. So thank you for that.
Yeah. Thanks. So I tried to understand the original implementation, and I have to admit I got lost somewhere in the specification of the algorithm in this configuration file. But as far as I know, you still perform two separate backprop steps in the original implementation. Can you quickly comment on whether that is true or not?
It's an implementation detail of Theano, but basically there are two different backprop steps, but they were compiled into the same sort of run function, and therefore the updates occur sort of with respect to.
We should definitely talk offline on this. So
Yeah, sure.
I don't know whether it's different or the same or whether it's a superficial difference, but we only need one backprop. So, any more questions?
Hi, thanks Sebastian for the talk. My question was also on your intuitions on why actually divergences don't matter, the differences in divergences. So you always use the same network to model that T function, right, of 3 million parameters. So I guess you're not going to compare the different 3 million parameters for each divergence to see if they have like similar values and if divergence matters.
Well, the problem is what you would like to do is you would like to compare functions, and comparing neural network parameters as a proxy of comparing functions is hopeless. So we would have to compare the functions.
So you would have to like run a forward.
You could do this. There was some work a couple of years back from Yusha Benji's group where they looked at function evaluations on a holdout set and then used that response vector as a proxy for where you are in the function space. That would be interesting actually to revisit that paper in the context of GANs to explore for various divergences what are the
function. And also, so it would be a hack and not as theoretically as sound as what you just mentioned. But have you thought about at a certain point of training switching the divergence to see if it completely diverges or if the current T is also sort of relevant?
Yeah. So actually I have to defend the original choice of the Jensen-Shannon divergence here. It's the only one that yields a very nicely symmetric training objective. And for some divergences you actually get this f-star function being something like an exponential function, which could be difficult to handle numerically. So in that sense, from a numerical point of view, I have preference for certain divergences, including the Jensen-Shannon divergence. But other than that, yeah, it's to be seen.
Thanks.
We have time for one more question.
So, which of the two questions should I ask? I guess the one about the variational bound being more or less tight for different divergences. And is there anything that you can say about it works very well for X, but not so much for another divergence?
I mean, we have this univariate experiments, and there everything is easy and it works, right? But the complexity of the density compared to the number of samples which we have, which is infinite in this experiment, is very different from what we have for real tasks. So I don't want to make any statements along that line. It's too early to say. I mean, we will have, eventually over time, I think we will build an intuition as a community, but I don't have one, no. And that's the second question, or we wrap it up? Or? Second question?
All right, so that's also a comment on the, you didn't observe any difference between the different divergences. And I was wondering, even though the images look kind of the same, one difference that there could be is the difference in the entropy of these distributions and the diversity of the samples that you get. Do you also, do you confidently say that they are equally diverse?
Yeah, so that's a very interesting question, how to, I mean, visual quality inspection is one thing, right? If you can see visual differences, you have confirmation that they must be different. But if you can't see visual differences, it doesn't mean that they are not different or that certain modes are not there. And there's a very nice work recently that uses kind of a very computationally laborious experiment to compare these questions. So I'm certain they are different in some aspects. But one point I want to comment on is that these papers, including your blog posts and comments on the topic, have made is that we should see visually improved samples, for example, if we use a reverse KL, and that we don't observe. And so now the obvious question is, I buy the theoretical argument and the motivation that flows from it, but we don't observe this in the real model. So we are missing something, and what is this, what we miss? And I think it's that this current model, the Alex model, is a very good model, and it's good because also it has a strong inductive bias. That gives us nice images, but maybe there is something more to it.
All right, thanks. Let's thank the speaker one more time.